Hello everyone, please check if audio video is clear. Yeah, perfectly fine. Thank you very much. So let's begin the session. So this is the seventh lecture on the concept of set theory. Okay, so what are we discussing? Currently we are discussing the concept of sets and relation. We have studied the concept of sets, we have studied the concept of relation. Then we defined the concept of partial order relation and equivalence relation. Based on the partial order relation, we said that in a partially ordered set, if least upper bound as well as greatest lower bound exists for every pair of element, that we called a lattice. Then we defined different types of lattice, and we have already seen some of the types of lattices in the last class. Today we'll discuss some more different types of lattice, and then we'll end the session or we'll end the discussion of lattice with the discussion of Boolean algebra or Boolean lattice. Let's proceed further. So, we have already seen the definition of lattice in the last class. We have discussed the concept of bounded lattice, complement of an element in a lattice, and based on that, we have discussed the concept of complemented lattice. What are we going to discuss today? So, we are going to discuss some more types of lattices. So, namely, we'll discuss the concept of sublattice, lattice, and that's what we are going to discuss in today's class. So let's have a quick revision. What is a joint semilattice? Sir, a poset in which least upper bound exists for every pair of element. Least upper bound exists for every pair of element will be called a joint semilattice. So what is a meet semilattice? Meet is basically greatest lower bound. So a process in which greatest lower bound exists for every pair of element will be called a meet semilattice. If it is either a joint semilattice or a meet semilattice, then it will be called a semilattice. But to become a lattice, both least upper bound as well as greatest lower bound should exist for every pair of elements. So basically, if least upper bound exists for every pair of element, it will be joint semilattice. If greatest lower bound exists for every pair of element, it will be meet semilattice. So a poset which is both joint semilattice as well as meet semilattice will be called a lattice. Okay. So what did we say? Sir, this is just a note. You just need to remember the set of all divisors of positive integer n will form a lattice with respect to relation divide. Always. It is always true. Now, in a lattice, the least upper bound will be denoted using this symbol and the greatest lower bound will be denoted using this symbol. Now, there are certain properties which always holds true in a lattice. What are they? Sir, the binary operation least upper bound and greatest lower bound will be commutative. That is, whether you perform A least upper bound with B or B least upper bound with A will be same. A greatest lower bound with B and B greatest lower bound with A will be same. Now, the binary operation least upper bound and greatest lower bound are associative as well. The binary operation least upper bound and greatest lower bound follow the idempotent law. Means if you take the least upper bound of element A with A itself, then the result will be A. If you take the greatest lower bound of A with A itself, the result will be A. Apart from that, the least upper bound and greatest lower bound will also hold the absorption law. Okay, so this four properties will always hold true in any lattice. But you also know about the distributive property. So distributive property may or may not hold true in a lattice. If distributive property also holds true in a lattice, it will become distributive lattice. That's what we are going to discuss in the today's session. But so first type of lattice that we discuss is the bounded lattice. What is a bounded lattice? A lattice in which both upper bound as well as lower bound exists will be called a bounded lattice. Sir, what do you mean by upper bound and lower bound? So we have already discussed while we were discussing the Hasse diagram that if there is a unique maximal element, it will also be the maximum element, and that same maximum element will also become the upper bound of the lattice. Similarly, if there is a unique minimal element, it will also be the minimum element, and that minimum element will become the lower bound of the lattice. But in our POSET, it is not necessary that the maximum element or minimum element will exist. So it may be possible that there is no maximum element or there is no maximal element as well in the POSET. So in that case, it will not be bounded. So I have already given the example. I'll give you the intuition again. Sir, it's anyway. So what is our bounded lattice? Sir, our bounded lattice, in our bounded lattice, maximum element, if exists, will become the universal upper bound, and the minimum element, if exists, it will become the universal lower bound. The basic definition is that in your lattice L, if there exists an element I belonging to set L, such that if you take the least upper bound of any element of the lattice with I and it comes out as I only, then I is called universal upper bound of the lattice. Similarly, if there exists an element O belonging to set L such that if you take the greatest lower bound of any element of the lattice with O and the result is O itself, then O is called universal upper bound of the lattice. Basically, I is nothing but the maximum element, O is nothing but the minimum element of the lattice. Now, a lattice in which both universal upper bound as well as universal lower bound, that is a lattice in which both maximum as well as minimum element exist, will be called a bounded lattice. Now, there are some lattices which may not be bounded. Let's assume that if we take a set of all natural numbers with respect to relation less than equals to, then there is no maximum element in the set of natural numbers. There is no, the largest natural number does not exist. The largest natural number is unknown actually, right? So, the maximum element will not exist in this particular lattice. Is it still a lattice? Yes, sir. If you take any two natural number, one will be larger, another will be smaller. So the larger one will become universal upper bound and the smaller one will become universal lower bound. That's what we know. So set of natural number is a lattice, but upper bound of this lattice does not exist. What will be the universal lower bound? Sir, universal lower bound, the smallest natural number is 1. So universal lower bound will be equals to 1. Similarly, if you take the set of all integers with respect to less than equals to, then there is no smallest integer. There is a smallest natural number that exists and that will be 1. But there is no smallest integer and there is no largest integer. Therefore, there is no minimum element with respect to less than equals to in the set of integer, and there is no maximum element with respect to less than equals to in the set of all integers. Therefore, this is still a lattice. If you take two integers, larger one will become least upper bound and a smaller one will become greatest lower bound. So for every pair of element of integers, the least upper bound and greatest lower bound will exist, but minimum and maximum element will not exist. So neither universal upper bound exists nor universal lower bound exists. Clear? So it's not necessary that all the lattices are bounded. There are some bounded lattices and there are some lattices which are not bounded. So if the lattice is not bounded, then either the upper bound will not exist or the lower bound will not exist or both of them will not exist. In all three cases, it will be called unbounded lattice. Okay. Yeah, that's one thing. What did we say? If the lattice is unbounded, then it is guaranteed that the underlying set will be infinite set. You can actually see this set is an infinite set. This set is also an infinite set. So if the lattice is unbounded, then it is guaranteed that the underlying set will be an infinite set. But if the underlying set is an infinite set, then is it necessary that the lattice will be an unbounded lattice? No, sir. No. So if the lattice is unbounded, then the underlying set is infinite. It's okay. But converse of the statement need not be true. That is, even when the set is infinite, then also the lattice may be bounded. So this is an infinite set. There are infinite real numbers between 0 and 1. There are infinite real numbers between 0 and 1. And with respect to less than equals to, the minimum element will be 0 and the maximum element will be 1 with respect to real numbers. Take any two real numbers between 0 and 1, the least upper bound and greatest lower bound will exist. But if you compare any real number between 0 and 1 with 1, the maximum element will be 1. If you compare any real number between 0 and 1 with 0, the minimum number will be 0. Therefore, the minimum element and maximum element exists in this case. Therefore, it is a bounded lattice. Clear? Now then we define the concept of a complement. Complement is only defined with respect to bounded lattice. If the lattice is not bounded, no element will have a complement. If the lattice is not bounded, then no element of that lattice will have complement. Clear? Okay? Okay, sir. Lattice is not bounded because the definition of complement itself depends on the existence of I and O. So if there are two elements A and B such that the least upper bound of A and B is equals to maximum element of the opposite, that is greatest element of the opposite, that is the universal upper bound of the lattice, or if the greatest lower bound and if the greatest lower bound of A and B is equals to O, that is the minimum element of the opposite, then A and B will be called complement. A and B will be called complement of each other. Now you just need to understand that in a lattice, complement of an element need not exist. It is not necessary that complement of all the elements will exist in a bounded lattice. No, it's not so. Okay, so it is not necessary that the complement of each and every element will exist in a bounded lattice. And even if it exists, then it need not be unique. Even if it exists, it need not be unique. That is, in a bounded lattice, the number of complement for an element may be 0, maybe 1, maybe 2, maybe anything up to the total number of elements minus 1. Yeah. Anyway, don't go about that. So in a bounded lattice, complement of an element need not exist, and if exists, then it need not be unique. That is, there may be 0 or more complement for an element of our lattice. Okay. Now what, sir? Then we define the concept of a complemented lattice. That do we have some lattices in which every element will have at least one complement? Yes, there are some lattices in which every element will have at least one complement. So if there is any lattice in which every element has at least one complement, will be called a complemented lattice. So if complement exists for every element of the lattice, then it is called a complemented lattice. Then it is called a complemented lattice. In a complemented lattice, every element has a complement, but it need not be unique. Every element will have at least one complement, at least one or more, need not be one all the time. So I believe I give the examples as this, the complemented lattice. This is also a complemented lattice. In this case, every element has exactly one complement. One, O, I, I. So in this case, complement of O will be I, complement of I will be O, complement of A will be B, complement of B will be A. Similarly, in this case, complement of O will be I, complement of I will be O, complement of A will be B and C, complement of B will be A only, complement of C will be A only. So every element has at least one complement. In this case as well as in this case, exactly one is also satisfying the at least one condition. So every element has at least one complement. Therefore, these lattices are known as complemented lattice. Okay, so these are some concepts which you need to understand, that if you think of a totally ordered set, then in that totally ordered set, if it is bounded, then the complement of universal lower bound will be universal upper bound, and complement of universal upper bound will be universal lower bound. That is, O complement will be I complement will be O, and complement will not exist for any other element in the totally ordered set. Complement will not exist for any other element in the totally ordered set. I have already given you the concept that if you select an element above X in the totally ordered set, then it cannot be the complement, because the greatest lower bound with X will be X only, it can never become O. If you take any element below X, then the least upper bound of that element with X will be X only, it can never become I. Therefore, the complement of X cannot exist. Complement of an intermediate element in a totally ordered set cannot exist. Clear? Now, apart from that, I also explained one concept, that a complement of an element cannot exist on the same line. Complement of an element cannot exist on the same line as long as that element is not the universal upper bound or universal lower bound. Clear? Okay. So let's try to understand. So these are some examples I just gave you. These are all the complemented lattice. These are all the complemented lattice. Now let's try to understand the new definition. Let's start today's topic. Today's topic will be the very first type of lattice which we are going to discuss is the sublattice. And the definition of sublattice is very tricky. So please try to understand this definition carefully. Resume. What is our sublattice? Let set L with respect to the upper bound and greatest lower bound denoted by them. So let this be a lattice. Now L is the underlying set. What is L in this case? Sir, L is the underlying set. So a subset M of a subset M of set L such that such that elements of set M with respect to least upper bound and greatest lower bound follows the properties of a lattice such that M with respect to least upper bound and greatest lower bound the lattice is called sublattice. Come on, is called sublattice of lattice L only if only if for every pair of elements in lattice for every pair of element in lattice M, the least upper bound and greatest lower bound for that pair of element is exactly same as lattice. Come on. So the definition is tricky. That's what I said. The definition is tricky. So what is tricky here? If you take a lattice L, if you take a subset from the set L, then it's not necessary that the subset with the same definition of least upper bound and greatest lower bound will follow the lattice property. What does it mean? So the very first thing is that if you choose a subset M from set L, then first of all, the subset M should be of the type such that for every pair of element of that subset M, the least upper bound and greatest lower bound should exist in set M itself. That is, first of all, it should be a lattice. If it is not a lattice, then there is no point of becoming a sublattice. So first of all, M should be a lattice. Subset M should be a lattice with respect to same definition of least upper bound and greatest lower bound. Apart from that, for every pair of elements belonging to set M, the least upper bound and greatest lower bound will exist. It is guaranteed because it does not. If it does not exist, it will not be a lattice. So it is guaranteed that for every pair of element of set M, the least upper bound and greatest lower bound will exist in set M. But the least upper bound and greatest lower bound for every pair of element of set M should be exactly same as the least upper bound and greatest lower bound for that pair of element in lattice L. In lattice L. Clear? So I would rather define this definition in a different way so that it is more understandable. So let's try to understand. Let L with respect to this be a lattice. A subset M of set L is called a sublattice of lattice L, called a sublattice of lattice L only if First condition that this subset must be a lattice only if least upper bound and greatest lower bound exist for every pair of elements for every pair of elements of set M in set M. So for every pair of elements of set M, the least upper bound and greatest lower bound should also exist in set M. What does it mean? So simply if you try to understand, that is M should be a lattice. That's the first thing. M should be a lattice. If the subset itself, so if the subset is not a lattice, then forget about that. It can never become a sublattice of the original lattice L. Second, the least upper bound and greatest lower bound are upper bound and greatest lower bound for every pair of element of set M, for every pair of element of set M should be exactly same as least upper bound and greatest lower bound for that pair of element in lattice L. Okay, let's try to understand with the help of an example, so more clear. Consider the following lattice L. L. This is your X, this is your Y. Cool. So this is your lattice L. This is a lattice L. Now the question is, which of the following is a multiple select question? Which of the following is a sublattice of lattice L? First one. If I select a subset L1, if I select a subset X L1 from set L as X, A, B, Y. So I just want to check whether this X, A, B, Y will be a sublattice of this lattice L or not. So how many elements? So there are 3, 3, 6, 7 elements. So out of this element, 7 elements, if we choose X, A, B and Y, then will it be a sublattice of lattice L? Second, if I choose another subset X, A, y. Will it be, call it B? Is L3 X Y. Uh, y. So, if you want to check whether the given subset is a sublattice of lattice or not, so first of all, try to construct the Poset diagram for this subset with respect to same relationship. Okay. So, what do we know? Sir, X is the minimum element. So, here also the X will be the element. Now, what? Sir, in this original lattice, X comma A belong to relation R. Therefore, here also X will relate with A. X will relate with B. So, X will relate with B as well. Now, sir, please tell me, A relates with Y in this lattice or not? So, please try to understand there is no direct edge between A and Y because A and Y are related transitively via D and C. So, A relates with D and D relates with Y. Therefore, we don't need to draw an edge between A and Y. Similarly, A relates with C and C relates with Y. Therefore, we don't need to draw an edge between A and Y. But in this particular set, neither D is present nor C is present, but A is still related with Y. Come on, guys, come on. Let's try to understand. If I say that 1 is less than equals to 2, 2 is less than equals to 3, and 3 is less than equals to 4. So I know that 1 is less than equals to 2, 2 is less than equals to 3, and 3 is less than equals to 4. So 1 will be less than equals to 3 and 1 will be less than equals to 4. So what if 2 and 3 are not present? So if 2 and 3 are not present, then also if 2 and 3 are not present, then also 1 will be less than equals to 4. That means then also 1 will relate with 4. Even if 2 and 3 are not present, then also 1 will relate with 4. So that's the same concept that we are going to apply. That in the original lattice, A relates with Y, but we are not showing that explicitly in the Hasse diagram because the transitivity is implied in the Hasse diagram. We don't need to represent it explicitly. But here, there is no other element which relates with A and that element relates with Y. Therefore, we'll have to draw a direct edge from A to Y, similarly from B to Y. So first of all, check whether L1 is a lattice or not. Yes, sir, it is a lattice. For every pair of element, these upper bound and greatest lower bound exists in this Hasse diagram. Therefore, it is a lattice. Okay. So L1 is a lattice, is fine. But is L1 a sublattice of L? Is L1. So there are two conditions. First of all, that the subset should be a lattice. Subset should be a lattice. So first condition is satisfied that yes, sir, this subset L1 of set L is a lattice. But still, we don't know whether L1 is a sublattice of L or not. To check whether L1 is a sublattice of L or not, we need to make sure that least upper bound and greatest lower bound for every pair of element of this set L1 should be exactly same as the least upper bound and greatest lower bound for that pair of element in L. But do you realize one thing? That's what is the least upper bound of A and B in the original lattice? So the least upper bound of A and B in the original lattice is C. So there are two upper bounds of A and B. A and B join each other at C and A and B join each other at Y. So both C and Y are the upper bounds of A and B. But among those upper bounds, C is the least of those two upper bounds. So the least upper bound of A and B will be C in the original case. In this case, what is the least upper bound of A and B? So in this case, least upper bound of A and B is Y, not same as L. Not same as L. Therefore, subset L1 is not a sublattice of L. That's what you need to understand. That first of all, your subset should be a lattice, and apart from that, for every pair of element of that subset, the least upper bound and greatest lower bound should be exactly same as the least upper bound and greatest lower bound for that pair of element in the original lattice. But yeah, it is not the case. Let's look at the second one. Son 𝐂𝐸𝐬𝐷𝐸. Okay. So what will happen with respect to this? So this is your X. X relate with A, relates with Y. So here also X, A, C and Y are on the same line. So in the subset also they will appear in the same manner. X, A, C, Y will be on the same. Now my question is, if you take any two element on this line, if you take any two element on this line, the element on the upper side will be least upper bound and the element on the lower side will be the greatest lower bound. Similarly, if you take two elements on this line, then the elements on the upper side will be the least upper bound and the element will on the lower side will be the greatest lower bound. So you just need to understand that if you choose elements on the same line, their least upper bound and greatest lower bound is not going to change. The least upper bound and greatest lower bound is not going to change. So, sir, first of all, is it a lattice? Yes, sir. For every pair of element, the least upper bound as well as greatest lower bound exists. Take any two element, the element on the upper side will be the least upper bound. The element on the lower side will become the greatest lower bound. So, for every pair of element, least upper bound and greatest lower bound exists. So, if you take x and c, then the least upper bound of x and c is c. Here also, if you take x and c, then on the same line, c is on the upper side and x is on the lower side. So, the least upper bound of x and c will be C and the greatest lower bound of x and c will be x. So obviously for every pair of element, the least upper bound and greatest lower bound will be exactly same as lattice L. So L2 is a sublattice of L. Choose any two elements on this line. The least upper bound and greatest lower bound will be defined by the element in such a way that the element which is on the upper side will become least upper bound and element on the lower side will become greatest lower bound. Here also they are on the same line, so nothing is going to change if the elements are appearing on the same line in both the Hasse diagram. Okay, let's look at the third one. Sir, x c d y, c d x relates with c. Yes, sir. Come on, this will be interesting to watch. Sir, does x relates with d? Yes, sir. X relates with a and a relates with d. Therefore, x relates with d. X. Okay, sir. Does x relates with c? Yes, sir. X relates with a and a relates with c. Therefore, x relates with c. Or x relates with b and b relates with c. Therefore, x relates with c. But that relationship between x and c is not represented in this poset diagram because of presence of a and b. In this subset, neither a is present nor b is present. Therefore, we'll have to draw a direct edge from x to c. Now what? Sir, d relates with y. Yes, sir. C also relates with y. So both d and c will relate with y. Both d will relate with y. Now please tell me, this L3 is a sublattice or not? Yes, sir. It is a sublattice. For every pair of element, least upper bound and greatest lower bound exist. Now, is it a sublattice of lattice L? That's what we need to check. Come on. If you take three elements on this line, x dy, nothing is going to change. If you take three elements on this line, nothing is going to change. But what if you take the elements from two different lines? The least upper bound of d and c is y. Here also, the least upper bound of d and c is y. But in this case, the greatest lower bound of d and c is a. Greatest lower bound of d and c is a, whereas in this case greatest lower bound d equals to x, not same L. Not same as L. So option C is also therefore not a sublattice. Okay, sir. So the last one is 𝐂𝐸𝐬. I'll try to draw it here because I don't have sufficient space. The other side. So this is your x. Yes, sir. 𝐂𝐸𝐬. 𝐂𝐸𝐬. X relates with A. Yes, sir. Here also it will. X relates with E. Yes, sir. X relates with B and B relates with E. Therefore, X relates with E. Now, A and E are not related. A relates with Y via D and C, but here neither D is present nor C is present. Therefore, A will relate with Y. E relates with Y. Here also E will relate with Y. So, is it a lattice? Yes, sir. It is a lattice. It is a lattice. If you take any two elements on that particular line, X, A, Y, no least upper bound and greatest lower bound is going to change. If you take two elements on the line X, C, Y, least upper bound and greatest lower bound is not going to change. Let's check for A and E. So what is the least upper bound of A and E? So A and E join each other at Y. Therefore, upper bound of A and E equals to Y here also, and here also is the upper bound of A. Similarly, sir, where do they meet each other? At the lower side. So the greatest lower bound of A and E is X. Here also the greatest lower bound of A and E. So for every pair of element, the least upper bound and greatest lower bound, for every pair of element of this subset L4, for every pair of element of this subset L4, the least upper bound and greatest lower bound is exactly same as the lattice L. Therefore, option D, that is the subset with respect to option D, is also a sublattice of lattice L. So two correct choices. Option B is a sublattice of lattice L. Option D is a sublattice of lattice L. A and C are not the sublattice of lattice L. Clear? So I hope you have understood the concept of sublattice. Now the last slide I have just next is the distributive lattice. Sir, what is a distributive lattice? We have already understood the concept of complementary lattice, right? So it's dependent on the definition of complementary lattice, but the basic definition will be, first let me explain the basic definition, that we are never going to use to check whether the lattice is a distributive lattice or not. But that's actually the definition for a distributive lattice. What does it say? Let the set L with respect to least upper bound and greatest lower bound be a lattice. Lattice L is called a distributive lattice. Lattice L is called a distributive lattice if and only if, or if following properties holds true. What? The least upper bound of A with the greatest lower bound of B and C equals to for all belonging to set L. That is, this is what's a distributive property. So when do we say that a lattice is a distributive lattice? When do we say a lattice is a distributive lattice? In a lattice L, if distributive property holds true for every triple of elements of that lattice. In a lattice L, if distributive property holds true for every triple of elements of lattice L, then lattice L will be called distributive lattice. But this is quite clumsy to check that, sir, if you have 6 elements, let's assume you have 6 elements in the lattice, then in how many ways you can choose 3 elements out of 3 elements? 6, 5, there are 20 different ways. So, will you go for 20 different triples and check whether these two properties are satisfied for each one of those 20 triples or not? It will be very time taking, right? So, therefore, we do not use this property. I mean, it's fine that this is the basic definition of a distributive lattice, that a lattice will be called distributive lattice if distributive property holds true for every triple of that lattice. But to solve the equations, what will we do? Sir, note, in a distributive lattice, In a distributive lattice, every element of the lattice has at most one complement. Come on, what did we say? In a normal lattice, the number of complements for an element can be anything. There is no restriction. 0, 1, more than 1, no restriction. In a complemented lattice, every element should have at least one complement. Every element should have at least one complement. In a distributive lattice, every element of the lattice has at most one complement. So, in a lattice, if every element, come on, in a lattice, if every element has at most one complement, then will it be a distributive lattice? A distributive lattice, every element of lattice has at most one complement. If there is two or more complement for any element, then it cannot be a distributive lattice. So, in other words, that is, if there exists two or more complements, there exists or more complement for any element, then corresponding lattice is not a distributive lattice. Yeah. So let's look at the example. So please check how many complements. So please try to understand. Every totally ordered set is a distributive lattice because no element will have more than one complement. Every totally ordered set is a lattice. Okay, next. Look at this. So in the previous example, if you look at every element has 0 or 1 complement. Realize 1. 0 complements for some element and for some complements exactly 1 complement. It is necessary or sufficient condition? No. No GATE CSE 2025. You are talking about this. It is not a necessary and sufficient condition. No. If opposite will be true, if you say that there is any if there is any element for which there are two or more complements, then it will never be distributive. That is fine. That's what I read. If there exists two or more complement for any element, so this is sufficient. If there exists two or more complements for any element, then corresponding lattice is not a distributive lattice. It is guaranteed. It is guaranteed that if in the lattice any element has two or more complement, then it cannot be distributive. But there may be a situation when there is no complement for the element, then also the lattice is not distributive. So it's a tricky one. Sir, is every non-complemented lattice is distributive? No. No, 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 no. No GATE CS 2025. You come on, let me give you an example if you are struggling with that. I'll explain in a while. Okay, let me first complete the topic, then I'll give you the intuition that it's not necessary that if the lattice is not a complemented lattice, then it will be distributive. No, come on. So we only said one thing, that in a lattice, in a distributive lattice, there cannot be more than one complement for any element. Please, you understand if and then? In a distributive lattice, there cannot be more than one complement for any. If there exists any element for which there are two or more complements, then it cannot be distributive. As simple as that. Did I say if and only? So I said one thing. In a distributive lattice, every element of the lattice has at most one complement. That is, no element of the lattice can have more than one. If at all any element has more than one complement, then we distribute. But we are not saying that if every element has at most one complement, then it will be distributed. Come on. In a distributive lattice, every element of the lattice has at most one complement. But if every element has at most one complement, then it may or may not be distributive. If every element has at most one complement, then it may or may not be distributive. But with respect to totally ordered set, we can guarantee this, because in a totally ordered set, if you take any three element on this line and if you check the distributive property, it will hold true. If you check with respect to distributive property, it will hold true. So every totally ordered set is a distributive lattice. There is no doubt in that. This is sufficient. This is sufficient. If the lattice is a totally ordered set, that is guaranteed that it will be distributed. It is sufficient for the lattice to be distributed. If it is a totally ordered set, then it is sufficient for the lattice to be distributed. Make sense? Yes, to check distributive, we need to check complements. Right. Okay, that's one. Let me explain some other important things, then be able to give the answer of your question. Let's look at this. So, if I look at this, this is O I A T. Is it a distributive lattice? Yes, sir. It is a distributive lattice. O complement is I complement is O, A complement is B, complement. So every element has exactly one complement. So in this case, every element has exactly one complement, and apart from that, please try to understand, if every element has exactly one complement, it will be sufficient for to call it a distributive lattice. There is a specific situation in which that if and only if condition will not satisfy. Therefore, we do not say that it is a sufficient condition. But if every element has exactly one complement, it will be sufficient for it to be distributed. It will be sufficient for it to be distributed. It will be more precisely complement as well as distributed. Yeah? So every element has exactly one complement. It is also a complement because of this. It is also a complement. It is also a complement. In a while, I'll explain. Let me copy this and put it somewhere else. Right, sir. It is also. So, every element has at most one complement. Take any three element. Take any three element. Those three element will satisfy the distributive property. Therefore, is a distributive lattice. Here also, if you choose any three, come on. If you choose three elements on this line, they will always satisfy the distributive property. If you choose three elements on this line, they will also satisfy the distributive property. The only condition is that if you choose two from here and one from remaining two, then it will also satisfy the distributive property. You can cross check that, check ABI and or ABO, and you will be able to see that distributive property is satisfied for all the triples within this lattice. What are you saying? So every complemented lattice having exactly one complement, yes, will be distributed. Yes. Okay. Let's take one more example. Look at this. Please try to understand. We know that for O there will be only one complement I. For I there will be only one complement O. But what are the complements of A, sir? There are two complements of B and A, and there are two complements of A, and those are B and C. Therefore, not a distributive lattice. If any element of the lattice has more than one complement, then it is sufficient to say that that particular lattice is not a distributive. Similarly, here also A complement equals to, therefore not a let me give them two names. This is, let's say, assume L1. This is, let's say, assume L2. These two are very important lattices with 5 elements. Go and note down certain points. What? Note. Every lattice with 4 or less elements. These are the properties which we can prove, but we are not going to put here on the. So every lattice with 4 or less element is always a distributive lattice. So in the previous slide, I have defined two lattices L1 and L2. So L1 and L2 are the only two lattices, with 5 elements which are not distributive. L1 and L2 on the previous slide, let me write it. Are the only two lattices with 5 elements which are not are not third. Now I'm going to write an important thing. A lattice L, this is if and only if. This is sufficient condition. A lattice L is not a distributive. A lattice L is not a distributive if and only if it has a sublattice. If and only if it has a sublattice. We have also introduced the concept of sublattice, right? Only if and only if it has a sublattice is isomorphic. Isomorphic means isomorphic to L1 or L2. L1 or L2, the lattices on the previous slide. So, any lattice with 4 or less element will always be distributive. The only two lattices with 5 elements which are not distributive are L1 and L2, which I have drawn on the. Apart from that, any lattice L will not be distributive if and only if it has a sublattice. If and only if it has a sublattice which is isomorphic to L1 or L2. If there is no sublattice in lattice L which is isomorphic to L1 or L2, then that lattice will be distributed. Yeah. Okay. Now, sir, why do you say that it is not a sufficient condition? Try to understand. Look at this particular posted diagram. Let's assume that this is an unbounded lattice. Let's assume that this is an unbounded lattice. 𝐂𝐸𝐴 2025. Let's assume that this is a lattice. Is it a lattice? Yes, sir, it is a lattice. What's wrong with that? It is a lattice. So it is a lattice. Now, in this lattice, do we have universal upper bound and universal lower bound? Sir, we do have universal lower bound, but we do not have universal upper bound. So, is there any complement for any element of this lattice? Do we have complement for any element of this lattice? No, sir. We do not have complement for any element if the lattice is not a bounded lattice. So, no element has a complement. So, no element has a complement means every element has at most one complement. So, when we are saying every element has at most one complement, should it be distributive? No, it is not sufficient. If you look at this closely, and we have a sublattice in the lattice which is isomorphic. We have a sublattice in this lattice which is isomorphic to L1. Therefore, this lattice is not distributive even if no element is having more than one complement. No element in this lattice has more than one complement. No element in this lattice has more than one complement. But still, it is not distributive. But still, it is not distributive because there is a sublattice of this lattice is isomorphic to L1. Here, every finite lattice is bounded. Yes, every finite lattice is bounded. But it is not finite, right? Clear? So, these are some points which you need to remember. Uh, let's, please tell me. D12 with respect to divide is distributive lattice or not? Somebody asks you like this. You check. I already know the opposite diagram, therefore I am dielectric. Don't worry. 1, 2, 12. So what? 1 complement 12, 12 complement 1. So 2 complement. So 2 complement does not exist. 6 complement does not exist. Okay. What about 3 complement? The 3 complement. What about 4 complement? 4 complement. These are the complements. So every element has at most 1 complement. Every element has at most 1 complement. Is it a distributive lattice? I don't know, because this condition alone is not sufficient. This condition alone is not sufficient to check whether this lattice is a distributive lattice or not, right? But it is a distributive lattice. Do we have any sublattice which is isomorphic? Do we have any sublattice which is isomorphic to L1 or L2? Do we have any sublattice which is isomorphic to L1 or L2? So, if I take a subset that is 1, 2, 4, 3, 12, then it is actually isomorphic to L2. Yes. Isomorphic to L2. But is it a sublattice of this given lattice? So what is the least upper bound of 2 and 3? Least upper bound of 2 and 3 is 6. In this case, what is the least upper bound of 2 and 3? Not same as E12. Therefore, not a sublattice. What can we say? Sir, isomorphic to L2, but not a sublattice. So this will not satisfy, because what did we say? That L1 or so our lattice L is not a distributive if and only if it has a sublattice which is isomorphic to L1 or L2. So there is a subset which is isomorphic to L2, but it is not a sublattice of original lattice. It is not a sublattice of original lattice. Do we have any other sublattice of L, or of let's call it D12? Do we have any other sublattice of D12 which is isomorphic to L1 or L2? No, sir. No. No sublattice of 12 is isomorphic to L1 or L2. That is, no sublattice of or given lattice is isomorphic to L1 or L2. Therefore, D12 divide is distributive. Clear? Because it will not be distributive if and only if it has a sublattice. There is no sublattice which is isomorphic to L1 or L2. Therefore, distributive or not? Distributive. Clear? So you will have to apply some logics before you say whether a given lattice is or not. But in a lattice, if any element has more than one complement, then it is guaranteed that it will not be distributed. Next one is Boolean algebra or Boolean lattice. So what is this? A lattice is both complemented as well as distributive. Is called Boolean lattice or Boolean algebra. What can we say? In a Boolean algebra, every element has exactly one complement. Every element has exactly one complement. So that's what, sir. This is a lattice. Is it complemented? Yes, sir. Every element has exactly one complement. Every element has exactly one complement. So at least one complement, at most one complement. Both the properties are satisfied. Therefore, it is. Yes. Okay. What else can we define? Note down. If n is a positive integer, such that dn, the set of all divisors of n, such that dn has no element the perfect square. Obviously, in the set Dn, 1 is also present. So, we are not including 1 except 1. If Dn has no element which is a perfect square except 1, 1, then set Dn with respect to divide is a Boolean algebra. The Boolean algebra where for an element x belonging to Dn, the complement of x will be n by x. Complement of x will be n by x. So this will always hold true. Don't worry. I have an example for that. If I take D21, so what is D21? So D21 is 1, 3, 7, 21. No element is a perfect square. Element except 1 is a perfect square. Therefore, D21 with respect to divide is a Boolean algebra. What are the complements? Sir, one complement will be 21 by 1, complement will be 21 by 3, 21 will be 1, 21, complement will be 21 by 3, that is 7, 7 complement will be 21 by 7, 21 complement. Even if you don't remember that property, then also you can answer 1, 3, 7, 20. This is a Boolean algebra. This is a Boolean algebra. One complement will be 21, 21 complement will be 3. But this is a direct property. If somebody asks you related to property, you should be able to give the answer. You should be able to give the answer. If Dn has no, such that Dn has no element which is a perfect square, then Dn with respect to divide is a Boolean algebra. Clear? So that will be all with respect to all the concept of sublattice. So we have already understood. No, sir. No. So we are done with all the concept related to set theory. So we have discussed set, we have discussed the concept of relation, equivalence relation, partial order relation, all the different type of relation. Based on the partial order relation, we have understood the concept of poset. Based on the concept of poset, we have understood the concept of lattice. Based on the concept of lattice, we have defined different types of lattices. And we have also understood the concept of complement of an element in a lattice. So today we have understood the concept of sublattice, concept of distributive lattice, concept of Boolean algebra, and with that we end the first part of the first chapter of set theory and algebra. So set theory and algebra will include three different topics. What are they? First, sets and relation. Second will be function. Third will be group theory. So we are done with the sets and relation. From tomorrow we'll start with the function. It will take only 1 or 2 class for function, and then we'll discuss the concepts of the group theory. Clear? So that will be all for today's session. Thank you very much for joining. Keep learning, keep practicing. Have a good day.